Hey there, this is Andrea with my week 6 advanced interactive concept. Um, there is no presentation, so I'm just going to do a PowerPoint and kind of read off of that for what I put together. So let me get out of here. And okay, so move myself away. This is the chemistry of a nuclear bomb. So the modern nuclear weapons work by combining explosives, nuclear fission, and nuclear fusion. The explosives compress nuclear material, causing fission. The fission releases massive amounts of energy in the form of X-rays, which create the high temperature and pressure needed to ignite fusion. So fission, during fission, the nuclei of certain heavy atoms split into smaller, lighter nuclei, releasing excess energy in the process. This can sometimes occur spontaneously, but can also occur um, in certain nuclei be induced from outside. So a neutron is shot at the nucleus and it's absorbed, causing instability and fission. And some elements, such as certain isotopes of uranium and plutonium, which is what we see pretty much with all the nuclear weapons, the fission process also releases excess neutrons, which can trigger a chain reaction if they're absorbed by nearby atoms, which is pretty much what happens. Just so some bullet points to summarize it real quick. Nuclear fission is a process where the nucleus of an atom is split into two or more smaller nuclei, which is known as fission products. The fission of heavy elements is an exothermic reaction, and huge amounts of energy are released in the process. Nuclear fission occurs with heavier elements where the electromagnetic force pushes the nucleus apart, uh, where the electromagnetic force pushing the nucleus apart dominates the stronger nuclear force holding it together. So, in order to initiate most fission reactions, an atom is bombarded by a neutron to produce an unstable isotope which undergoes fission. When neutrons are released during the fission process, they can initiate a chain reaction of continuous fission which sustains itself. And then fusion works in reverse. So when exposed to extremely high temperatures and pressures, some lightweight nuclei can fuse together to form heavier nuclei, releasing energy in the process. So in modern nuclear weapons, which use both fission and fusion, a single warhead can release more explosive energy in a fraction of a second than all the weapons used during World War II combined. So atomic bombs are made up of a fissile element, which usually uranium, that is enriched in the isotope that can sustain a fission nuclear chain reaction. So when a free neutron hits the nucleus of a fissile atom like uranium-235, the uranium splits into two smaller atoms called fission fragments, plus more neutrons. So fission can be self-sustaining because it produces more neutrons with the speed required to cause new fissions. This creates a chain reaction. So all nuclear weapons use fission to generate an explosion. Critical mass depends on the density of the material. As the density increases, the critical mass decreases. So instead of colliding two subcritical pieces of nuclear fuel, modern weapons detonate chemical explosives around a subcritical sphere of uranium-235 or plutonium-239 metal. The force from the blast is directed inward, compressing the pit and bringing its atoms closer together. Once dense enough to reach the critical mass, neutrons are injected, initiating a fission chain reaction and producing an atomic explosion. So here we have a diagram of a thermonuclear warhead. So this is where fission is primarily occurring. Here's your neutron generator. Move myself out of the way here. So the explosions used in thermonuclear weapons are often described as a primary, which is what I pointed out here, chemical and fission explosions, and secondary, the subsequent fusion blast. However, the actual mechanisms are considerably more complicated. So, I'm going to put myself there. Okay. A nuclear weapon can either undergo a nuclear fission reaction, like an atomic bomb, or a nuclear fusion reaction, like an H-bomb or a thermonuclear bomb. The first nuclear weapons built underwent pure nuclear fission. Uranium-235 and plutonium-239 were the most common fissile isotopes used. Um, there are two basic nuclear fission weapon designs. So we have the gun assembly, which is right here. A uranium-235 bullet is fired through a barrel at a fissile uranium-235 target. The collision of the two isotopes initiates a chain reaction. The gun assembly design only proves practical when the uranium-235 isotope. So implosion, which is more common, especially like with the bombs, is a critical mass of a fissile material is surrounded by highly explosive material. So when detonated, the high explosives compress the fissile material, causing it to assume a state of supercritical mass. The supercritical mass instantaneously begins to undergo a chain reaction, and that's how the nuclear bombs essentially work. Oh, where'd it go? Oh no. Oh gosh, come on. And then here's my last slide. The implosion method is considered more sophisticated than the gun method and only can be used if the fissile material is plutonium. The inherent radioactivity of uranium will then release a neutron, which will bombard another atom of uranium-235 to produce the unstable uranium-236, which undergoes fission. So releases further neutrons and continues to process. The uranium atom can split any one of dozens of different ways as long as the atomic weight adds up to 236 uranium plus the extra neutron resources. Okay, thanks for listening.